Okay. Right. So this next session is on optimization and related rates. And so optimization problems make use of derivatives. And so we have, in terms of basic steps to solve them, decide what variables and constants, draw a diagram if appropriate, write a formula for the function in which you want to find, express it in terms of one variable, and then set the derivative equal to 0, and find the answer. So, for example, given something like this, have 100 feet of fencing, and want to make a rectangular play area alongside the wall of the house. So we have the house, we have a fence, and we're going to fence this in. We know that we have 100 feet of fence, so the perimeter is equal to 100, and we want to maximize the area of this. Okay. So if we call this x, and then this side would be x, and then this length will be 100 minus 2x. See, we know the perimeter is going to be all three sides added together. And so the area of my fence will be given by x times 100 minus 2x. So that gives me the area. And so if we do this out, we get that the area will be given by 100x minus 2x squared. So we got our drawing, we set up our variables. Our equation is in terms of only one unknown. So the next step in the process was to find the derivative. So if I take the derivative with respect to x, this will be 100 minus 4x. The next step in the process was to take that derivative and set it equal to 0, and then solve for x. So if I add 4x, add 4x, we get that 100 is equal to 4x. Next step, divide, and so x will be 25. And so we know that the sides are 25, and then the other piece will be 50. So 100 minus 2x gives me the other length. And so the dimensions will be 25 by 50. Okay. And so the area of this will be given by multiplying those two numbers together. And so the area is 1,250 square feet. And that's the area of this play area. Another type of problem is given one like this. So we got a box, piece of metal. Let's say this metal is 12 inches by 12 inches. And we want to make a box container. And by doing it, we want to cut out a square from each corner and a box. Okay. So each square will measure x by x for dimensions. So the length from here to here is going to be 12 minus 2x. From here to here will be 12 minus 2x. And we want to maximize the volume of our box. So the volume will be given by 12 minus 2x times 12 minus 2x times x. So the volume of a box is given by the length times width times height. So we got a drawing, we got our formula we're going to use, in this case volume of a box. Next thing you want to do is multiply this out. So B, if I first multiply the first two things together, we get 144 minus 48x plus 4x squared. Then we need to multiply that by x, so we get 144x minus 48x squared plus 4x cubed. And that'll be our equation. Again, next step is to take the derivative. So we take the derivative with respect to x. So dv dx is going to be 144 minus 96x plus 12x squared. Well, let's take this and rearrange it into the normal way of looking at a quadratic. Which will be like that, and set that equal to 0. Well, we look at our numbers. We got that 12 will go into everything, so let's take the 12 out. So we get x squared minus 8x plus 12 equals 0. That quadratic can be factored. Okay, still have our 12. We're going to get an x and an x. It's a plus 12, but it's a negative in the middle, so we need two negatives. And then we need two numbers, multiply together to give you 12, and have a total of 8. So that's going to be 6 and 2. And now we can solve this, so we get x minus 6 is equal to 0. X minus 2 is equal to 0. This one gives us x equals 6. This one would give us x equals 2. So we get two answers, but only one of these answers is indeed valid answer. Okay. So we need to check. So if we look at it, again, my piece of metal was originally 12 inches. And if we take 6 inches out of each corner, there is no metal left. And so the answer we want is going to be the 2 inches off of each corner. So if x is equal to 2, then 12 minus 2x is going to equal 8. And the dimensions of the box would be 8 by 8 by 2. So the dimension of our box will be given by that. So you got, in terms of optimization problems, making use of derivative. Next type of problems are called related rates. Type problems. So you get something that looks like this. So for example, let's say we have a circular plate. We have a circular metal plate where the radius r is equal to 4 inches and it is being heated. And so as it's being heated, it's going to expand, and the RDT is given by 0.5 inches per hour. Right? And I want to know what is happening to the area of this plate over time. So we got to, first off, it's the circle, so area is given by pi r squared. The next thing we want to do is take the derivative of everything, but with respect to time. And so we get dA dt is going to equal 2 pi r dr dt. Okay. So now we can find out how the area is changing. So dA dt is going to equal 2 times pi times 4 times 0.5. And so we end up that will come out to be 4 pi, which will be 12.57, and that will be inches squared, and that would be per hour. So the area is changing at a rate of 12.57 square inches per hour. So we have in terms of this one. So you can have the same type of problem, but if the plate's being cooled, and in that case, you have to make sure you put that in as a negative number, because then the plate will be shrinking. So let's have with this. A balloon what is the change in volume change in time when R equals 3 meters. Given that R dV dr dr dt equals 2 meters per hour. So in this case, we got a balloon, it's going to be a sphere, and so volume of a sphere is given by 4/3 pi r cubed. So again, we want to find a derivative with respect to t. So we have dV dt is going to equal 4 pi r squared dr dt. And now the matter of just taking our numbers and plugging in. And so we get that this will be 4 pi times 3 squared, and we said the rate was 2 times 2. So we plug that in, and we end up at and so that comes out to be 226.2, and this will be in terms of cubic meters per hour. So volume is in cubic units. So you have in terms of related rates and how one changes with the other. So the next bit is on what is called Newton's method. And so Newton's method is given by this. That x is given by x naught minus evaluated at the function evaluated at x naught divided by the derivative evaluated at x naught. So for example, we want to come up with the square root of 7. So x squared would equal 7, and solving that for 0, we get x squared minus 7 is equal to 0. So my function would be y equals x squared minus 7. And so my derivative would be 2x. So that's my derivative. And let's use as our initial value that x naught is going to be 2. So now we plug in to our method here. And so we have its x naught, which will be 2, minus f of x naught, which will be 2 times 2. Or sorry, it's going to be 2 squared, minus 7 over 2 times 2. So this will end up being 2 minus 4 minus 7 over 4. So we plug that in, and we get our next value. then that'll be 2.75. And then we would take this number, and now we put this in. And every time we do this, we would end up getting a better answer. And so we do this again. This number now comes out to 2.6477. And so if I keep on doing that, we keep on getting a better and better answer to what would be the square root of 7. Right? So there's a method. Again, this is back in the time of Newton when you didn't have calculators and just plug in and get the square root of 7. But even after 2 steps, I get 2.6477 and going. And if you compare that to what the toy gave me right away, this on the calculator becomes 2.6457. So even after just 2 times, I'm already fairly close to the value of what this should be. So we have in terms of Newton's method as a way of evaluating and quickly approximating what would be a value. And then the last part of what's in this chapter deals with linear approximations. So the last part. So let's go to the book here for a moment. So linear approximation of a formula. So this. Again. So linear approximation. Also x is given by the derivative evaluated a times x minus a. Okay. So we get in terms of what that formula. So let's look at example 1 here. So let's look at the square root f of x is square root of x plus 4. So let's say that f of x is equal to the square root of x plus 4. We can do the same thing as x plus 4 to the 1/2. Which means my derivative of this would be 1/2 x plus 4 to the minus half, right? Would be my approximation for this, right? So we got our derivative, and then let's use that, and let's follow the example in the book. And so they said to use this at x equals 5. At x equals 5. Right. So if we follow this at x equals 5, get in our equation, the derivative, evaluated a, So this will be L sub x is given by 1/2 5 plus 4 times x. Substitute that number. I'm sorry, I didn't put this in. Okay. All right. So back to linear approximation. So again, the linear approximation is given by the derivative evaluated at a times x minus a plus f of a. So let's look at an example here. So we got square root of x plus 4. So I can rewrite that by giving the radical. Okay. And then I take my derivative of that, and we end up with this as my derivative. So let's say I want to use this to get the square root of 9. Well, given 9, that would mean x is going to be 5. And so we plug this in. And so x is also going to be my a when I plug into that formula. So we get 1/2, 5 plus 4 to the minus 1/2, x minus 5 plus the square root of 5 plus 4. So this would be 1/2, this would be 1 over the square root of 9, changing that back, times my x minus 5. This would be the square root of 9, which is 3. Square root of 9 is 3, multiply that by 2, we get this, and so we get this formula that we can use. So now let's say I want to get an estimate of what is the square root of 10. Well, the square root of 10, for that, we would have that x is going to be equal to 6. And so we would have 6 minus 5 over 6 plus 3, and this would give us 3.1666. And we would end up with that as an estimate of the value of the square root. And if we check that against what the calculator says for the square root of 10, the calculator gives us 3.162277. And so we get a pretty good approximation as to the square root of 10 based on this. Right? The last other things in the chapter deal with a couple theorems dealing with calculus, and so we'll just put those up. And so you get Rolle's theorem, this is in the notes, which says basically if I have a function, it is continuous suppose that we have some over interval AB, it's continuous on the interval, f of a equals f of b. Then at some value, the derivative evaluated c is equal to 0. So we have it in terms of that theorem. And then other theorem they talk about in here is the mean value theorem. Both of these we've seen and we've actually used in this class already. And so the mean value theorem actually is our definition of what was a derivative. Again, this is just an equation that is slope. And with that, that will conclude this lesson.